have problem with translation. You don't see anything, yes?
Not yet.
Not yet. Okay, let me try again. Okay, now one way it doesn't work. Let me try another way. Oh, okay. I hope you see anything now. Okay, so first of all, I want to say that I put on the website notes of some previous lectures. I added three more. So overall, I wrote more than half of all lectures, and almost all which are already delivered. So you can find some new problems. And today's lecture number 12, and it will be one slide for these two lectures. Let me first recall where we are now. Last week we talked about Schur-Weyl duality. First of all, classical, then Q-deformed Schur-Weyl duality. So in the classical part, we have commuting action of the GLN and symmetry group. In the Q-deformed situation, we have commuting actions of the quantum group and Hickey algebra. And then we move to affine situation, affine, and from the very beginning, Q-deformed. So we have UQ of SLN hat. We consider its evaluation representation, and it is convenient for me to consider evaluation representation with formal parameter. This formal parameter is denoted by y, and the representation has a basis ei, where I runs through all integer numbers. So in original space, we have a basis E0, En minus 1. I changed a bit notation comparing to last week, but probably nobody noticed. And the integer base level by integers in the space is defined through this periodicity condition. And the action of the generators of the quantum affine SLN is given by this formula. In this base, which runs through integer. So you see this new basic elements, E, J, say, they have some sort of color. So if their index has a certain residue mod n, then the EI acts. Otherwise, EI acts by 0. And these colors appears everywhere in formulas. So now the colors are just residues mod n. I didn't check that this is actually that relations are fulfilled. This is straightforward, but that's the exercise. What else can I say? Maybe I should add that in this definition, representation is defined through its Drinfeld-Jimbo realization. So we don't have currents. We have just standard Drinfeld-Jimbo generators. Today we are going to talk about this some limit, and we will return to to new Dirichlet currents next week when we'll talk about Bosnianization, stuff like this. But today, so we don't use almost anything from the previous lectures. Okay. Some explanations which we give from before. And the algebra which commutes this quantum affine to SLN is affine Hecke algebra. There are different presentations of it, and we use this presentation with generators T1, Tn, maybe -1, and y's, y1, so yn -1, such that T's generate a finite Hecke algebra, so they satisfy quadratic relations and braid relations. Y's commute, and relations between T's and Y's are as follows. If a parameter of the Hecke algebra is equal to 1, then these quadratic relations become relations that T are involutions, T inverse equal to T. Then this relation will mean that T commutes with Y is different from I's and I plus 1. And this relation, here we can write T inverse, means that conjugation by T gives us from Y, I plus 1. And this is standard action of the Weyl group on the lattice of the weights. But it appears that in the Hecke story, we have not T inverse here, but just T. So only for Q equal 1, this relation can be viewed as literally as a conjugation. Okay, this is a Hecke algebra. And a theorem which was stated in the very end that there is an action of the affine Hecke algebra on the space Cn of y1, yn inverse, and this action commutes with quantum affine SLN. And the action is given as follows. So y's are y's. In our vector space, there's multiplication by y and y inverse from the very beginning. And t's are defined as follows. If we do not have y's, so we restrict ourselves to the not affine part of the space, just standard product of the standard basic vectors, then T acts as a R matrix, finite dimensional R matrix. And if we want to act by T on some other element, which is obtained from the original ones by action by Y's, then we should recommute T with Y's and then act. So this is the only extension of the action. If you assume that T acts on the standard Cn on this part of the space by finite dimensional R matrices, so this is the only extension of this. Of course, it is a statement that we actually have an action of the affine Hecke algebra, and it commutes with the QSLN, and this will be from the very beginning, right? So it will be a problem. This guess will be a problem, and maybe I should, but I don't know very good explanation of this fact. Just proof by calculation, and I will not do calculation in the lectures. I left this. Okay, this is more or less the point where we stopped last time. There was something about the affine matrix, but I will not recall this. Are there any questions? Okay, if there is no questions, let's move further. First, let me say, so I define T by some formula. There are some other formulas which can be helpful for this in this situation. So we can write T as more explicitly in the basis. Yeah, so it is sufficient. So here we consider a case where we have only two factors. So here, let me write it here, number of factors, which is n capital is equal to 2, and T, we have only, in this case, we have only one T, and T1 is not by T. But it is not important. If n is, for n is greater than 2, formulas will be similar, and I will explain it in a minute. But first, let me explain what's written here. So we act on the some basic elements, EH times EG, where I assume that G is greater or equal than H, and I write that G is H plus NK plus S, where N is Coxeter number of SLN, if you want this, because we have SLN. S is a residue, so some number from 0 to n minus 1, and K is a quotient. And in this formula, we have two cases. S is equal to 0 and S greater than 0. And all formulas look the same. So first of all, we have sum where we permute our basic vectors. So we have EH and G, on the right side we have EG, AH. And here we have opposite. And if S equal to 0, then after permutation, we have some Q number, Q or Q inverse. If S greater is not 0, so residues of G and H are different, then we just permute. And there is some additional sum, certain additional sum, which goes over region depends on K, and more or less always something like from 1 to K, but there are some plus minus ones and so on. And terms here, they have the same residues as here, but they are somehow moved closed. So we can add to H some number of n's and G, and from second index we substitute NG. The sum of the indices remains the same. It is a gradient which we have on the whole space. It's always fixed. And this summation is how different. Are there any questions about this formula? I don't know. Do you want me to prove some of them? I do not plan, but I can.
Could you please show the previous page?
Previous page. What do you mean by previous page? This one or this one?
Okay, thank you.
This Q minus Q inverse comes, of course, from their matrix, from Q minus Q inverse, which we had in their matrix. This is, one can obtain this, for example, rewriting this formula or just by definition. And if n is greater than 2, and we act by some tk on some tensor product EG1, EGK, EG cap plus 1, tensor EN, sorry, EGN. Then obviously this is EG1 ej k minus 1, tensor t acting on this fact, on this part, gk tensor ejk plus 1. And then remaining basic vectors. So action of t is local. It acts on the only two consecutive factors. So actually, this form, it is sufficient. This formula knows all what we want about the action. And capital. This n, this is the same as here. We have SLN. So everything is periodic with somehow periodic or quasi-periodic with a period n. This is for affine SLN. This formula for affine SLN. I mean, in non-affine case, we have finite Hickey algebra. If you're asking me about wedges, antisymmetrizers, and stuff like this, then I will write formulas in a minute. But this is not disclosed, but different. If you're asking about just Hickey story, then in non-affine case, we can just, if you want to write out the action of the generator of the Hickey algebra, we should take formula for their matrix. This formula. And yes, this is more or less this formula, but after affinization, we have some big sums and stuff like this, yes. I'm really happy that I have some questions. If there are some more. Okay, if no, then this is where we are. Formulas for action of t. And what do you want to write in universal development? You're talking about finite case or affine case? In not affine case, we wrote down formulas for the R, but for evaluation representation, for fundamental representation. And in this case, the R satisfies quadratic relations. If you take another representation, it is not necessary to satisfy quadratic relations. It will not satisfy these quadratic relations, of course. So this Hickey property is a feature that we take special representations. And in this special representation, we have some sort of dual description using another algebra. This is a phenomenon of duality. Of course, you can take other set of other interesting representation, for example, another fundamental, and ask what will compute with a quantum group and so on. So I think people know something about this, but maybe I'm not ready to give answers. This is not about universal. This is not about universal matrix. I used universal matrix to write a formula for finite matrix in this case, but this is maybe overwork. I mean, this is not necessary. You can write a matrix which commutes with the Q of SLN in fundamental representations just by hands. And this is what people did 30 years ago. Okay. Okay. You're still here. I'm going to wedges. And This actually is, I mean, the main topic of today. So we state some theorems about this stuff and so on, but the stuff is actually the following. So let us define the following space: lambda nq of Cn y plus minus to be equal to the S minus applied to Cn, the n of y1 plus minus yn plus minus. Okay, I will not write this plus minus 1. Just so what is this? Is Q deformed? Stereo power. And maybe I should recall what is this. S minus is Q antisymmetrizer. Formula for it is S minus is a 1 over some n factorial minus summation minus Q in power minus L of W T W. Formula like this, but so since we so this is a certain element as a Hecke algebra. Since we know that Hecke algebra commutes with a quantum affine algebra, this subspace is invariant under the action of the quantum affine algebra. So this space which I defined is a representation of UQ SL. Okay, this first main layer of today. If we define the representation, it is natural to ask for a basis. Okay, let us introduce the good naive candidate of the basis. So let us definition. Is the following: E1 wedge EI2 wedge EIN. Let us define it as a S minus applied to the tensor product. In case of Q equal 1, these wedges form a natural basis in this space. Actually, this wedges form a basis if we consider E1, E2, En to be ordered, for example, increasing. Actually, the same holds in Q-deformed case, but before proving this, we need the following proposition. So we want to state that the elements of this form where i's are increasing form a basis. Why increasing? Why we can we in Q equal 1 case we can reorder them and get some signs. For in Q deformed case we know nothing about this, but I will now go into state this property. Yeah, if we take all such elements, they will generate this space, yes. But of course, they will be linearly dependent. If they are ordered, then it is not obvious that they generate the full space. Why? That's what we are going to prove. This is not obvious. It's not clear why. So we define some elements, and anyway, so I think the definition is should be more or less clear. So let me look to some notes where I want to find the formula. Okay, so I will now write the formula like this, and I keep the following notations. So that G is related to H by the same properties. Then I have some three cases. First, as before, let us assume that S equal to 0. In this case, EG, which EH equal to EH, which EG minus. So if G and H have the same residue mod n, then they're just like fermions, they anti-commute. B. Let us consider another somehow simple example where k is equal to 0. So it means that G and H, k is equal to 0 and S greater than 0. It means that G and H are now somehow close, have different residues, but very close. In this case, EG wedge EH is equal to minus Q EH wedge EG. So we can reorder them, we get the sign, but also if the residues are different, we get some Q. Let me look to some of my notes just to just to check that I'm not. Yes, it's okay. Okay, maybe it's not very important. But, in principle, I can make mistakes. Here it could be -1, but I look to my calculations. Looks everything's okay. And now C is some sort of generic case, and in this case, so generic means that K greater than 0 and S greater than 0. And in this case, the relation will be the most difficult. Not very, but so EG times EH is equal to minus Q. Again, we can recommute them. But now we will have some corrections. So minus EG minus NK wage EH plus NK and minus Q in opposite order. EH plus NK wedge EG minus NK. Okay, let me copy this formula in order to have it in one line. So, so what is the meaning? So we recommute them. We get Q since they have different order, and we get some terms which are closer, which actually closer to each other than we get before. So we get some. Let me write it. Draw some sort of picture. So get some H. Here's H plus N, here H plus 2N, say H plus 3N, and somewhere here we get G. And so we either reorder them or we replace them by this element, and correspondingly here we can write g minus 3n. Only here k is equal to 3. So these two elements belong to the segment from h to g, and they are close to each other. So I don't claim that now I reorder all elements in the increasing order. So these two elements are still decreasing. First index is greater than second, but they're close to each other, so I can use these relations again and again and reorder them.
Can you use these to relate like the second and the third? Aren't they like close enough to each other?
The second C is not generalization. B in C we have k greater than 0. B we have. Oh, okay. Okay. Maybe I want to. Maybe if I want to prove something today, I prove A. So we want to compute e.g. We want to compute e.g. wedge EH. This is some number. It is the action of 1 minus q inverse on t on e.g. tensor EH, just by definition. So this is equal. We have this number. And now, first of all, we have e.g. tensor EH. And then we get this q inverse t applied to e.g. times EH. And so we have to use this formula. So I will copy it. So get minus q inverse, and then the formula which I copied, and I hope will fit in this space, more or less. So here we computed one side. Now let's compute another side. EH wedge EG. Again, this will be a number times 1 minus q inverse t applied to EH tensor EG. Again, it will be this number. 1 gives us just 1, EH tensor EG, minus q inverse, and then I have to apply t to EH tensor EG. I go to the formula for action of t, find the corresponding element, and copy. This is our way to do calculations. And now we just have to compare these two terms. And what do we see? We see that the sums, they coincide up to sign and up to the fact that here we have extra term for g equals 0. And this extra term for g equals 0, it occasionally is like this. So here we have one coefficient, here we have minus q inverse, q minus q inverse, so this cancels, and as a result we get q in power minus 2, h tensor EG. And this actually agrees with this term. So what we get this is minus this. No, I'm wrong. This is minus this. This term is equal to this term plus g equals 0 terms here, again, percent, and this sums agrees. So as a result, we get what we expected. EG which EH equal to EH minus EH which And all other calculations are similar. Of course, I'm not going to do it. But are there any questions? Okay, if we believe in this fact, then we can state a corollary. Elements E1 wedge EIN generate nth power. Where I assume to be ordered. Proof. Using these formulas, we can reward the ice. We can reward the ice. If we after that reward we get two i's with equal indices, then due to this fact it will give us 0. So after this reorigin, we get i's after. So using this how it's called proposition. This proposition, this element generate this element generate what no, and a linear independence follows from the fact that for q equal 1 they're linear independent, so there couldn't be, so they're linear independent for generic q. Let me give one more comment that it is more or less clear, but since in commutation in the formal fraction of t, which we had here, we have q for in case where residues are equal, and in the case of different residues, t acts just by permutation. But in terms of wages, the situation is opposite. So if we have the same indices, we have same residues, they just like usual fermions, they anti-commute. When residues are different, we get Q. So for example, one can should have in mind that somehow the example of n equal 1, where we in something don't have quantum group. If QSL1, what is it? There's no such object. So we in this case we have only first case, so we have only fermions, as should be expected. Okay. Maybe I will need one more proposition about this fact. Okay, I stated explicitly, but then I explained its idea. Let some numbers E1, En be some integers such that their sum is less than n, and ij is less than n minus m. All this for some m. Then this weight is equal to 0. And the meaning of this theorem is the following. So we take this weight, and from this equation, it follows that all these i's are less than something. And if we then start to reorder them, here you see, I do not assume that they are ordered. They can either permute or move closer to each other, so they will still be less than this n minus m. But then from this condition, it will follow that it is impossible to have this the sum of indices, the gradient will remain the same, and after such reordering, we should get some new E1 prime wedge E prime with the same sum of indices, which will be ordered, which will be less than this, as well as this equation, and it is impossible to fulfill these equations. So it will be equal to 0. Okay, maybe I can't make it very clear, so I will skip and then return to whether we will. Okay. Are there any questions? As I said, the space is a representation of a affine quantum group. So it is natural to ask, can we write down this representation more explicitly? The answer is yes. Here I started to write down some formulas, but let me first explain. So I will, in the end of the lecture, today's lecture, we'll have some bases which will be labeled by Young diagrams, and I actually start to write down the Young diagrams. So for any partition lambda with L of lambda less than or equal than n, we can define the following vector: E minus lambda 1 minus m, which E minus lambda 2 plus 1 minus m, and so on. All this set of indices is increasing because of this sums. So if if L of lambda here I put strict inequality, but if I put a non-strict, then the last index will be minus lambda n plus n minus 1 minus n. Maybe I should write typical index here. Okay, let me do this. I enlarge in order to write down with more care. Wedge dot wedge E minus lambda j plus j minus 1 minus m. Wedge dot wedge E. This is how the typical. Now we want to act by.
What is m again? Is it an arbitrary integer?
M is some integer, yes. how to say, later we will come to the limit where n capital goes to infinity. And you know, in this limit, we have a basis of semi-infinite wedges, and these semi-infinite wedges have charge, have vacuums which are labeled by integers. And this m will be actually label of this vacuum.
Mm-hmm.
So if n will go to infinity, then this wedge will be e minus m plus 1, e minus m plus 2, and so on, up to infinity. So in order to have all such vacuums, I put here m, but of course this is just some complication. Okay, now I'm going to act on this vector by f, here I wrote already some formula, but maybe before it I should say the following. So if I act by f, okay, some other color, if I act by f on some ei1 wedge ein, so this is f s minus of ei1 tensor ein, since Hickey algebra commutes with a since Hickey algebra commutes with a quantum group, we can reorder and write here just Fi act on ei1 tensor ein. Okay, this is one, and second, this Fi is actually delta n of Fi. So in our convention of the coproduct, this will be Fi tensor 1 tensor 1 plus Ki inverse tensor Fi tensor 1 plus Ki inverse tensor Fi tensor 1 plus and so on, plus terms like this. After all this preparation, maybe we can read what I wrote here. So we act by Fi on this element. Using this property, which we can act first by Fi on this decomposable tensor, and then apply this antisymmetrization. Now let me recall that Fi acts on our basis as follows. It looks for the elements which have the same. Let me recall and find somewhere here. It looks for the indices which have the same residue mod n as I, and then substitute 1 from them. So in our formula, we look for the indices. So minus lambda j plus j minus 1 minus m is here. Maybe I can even copy it to make it more clear. So we look for these indexes, which are equivalent to I. And we substitute 1 from such indices. And we have some case in front of the f. This will lead us to Q in some power. I will talk about this power in a minute, but let's assume first that this is some combinatorial power. Now look on these two consecutive e's. Here is e's number j. Here is the previous one. But here we substituted 1. And if lambda j is equal to lambda j minus 1, then these two indices will coincide. And as we proved, if we have E which E of some E with same index, then this is actually 0. So this summation can be rewritten as follows. So we take summation over G, such that lambda J minus 1 has the same residues minus M minus I, and lambda J is strictly less than lambda J minus 1. And in this case, we just increase lambda J by 1. This is what's done in this formula. And I wrote it like this. So we add one box in this row of the partition lambda. This can be restated using the colorings. So this is an example where n equals 3 and m equals 0. We have some partition and color it by diagonals. 0, first, 2, 1, 0, and so on. And then we look to the all addable places, all places where we can, in principle can add box, and look to these places which has the color I. So this M should be hidden in the coloring of the angle of the diagram. So we take all boxes, all addable boxes, which of the color I. And on such box, we write Q in some power times lambda plus this box. So this is thing to take away. The action of the EI is given by the action EI at boxes of the color I, whether it's possible. Okay, with some facts which maybe just. Okay, now we can write down the similar formula for EI. So EI on lambda is equal to sum over S. Now summation will go over removable boxes of lambda, again of color I. Again, we get Q in some power, lambda minus this box. But there is some difficulty with E. And actually in this term, we have, in principle, we can have boundary term. What do I mean by the boundary term? So in principle, we can act by E on the last factor. We can and the last factor is n minus 1 minus m. E increasing so index. So after the action, we get n minus m, and this cannot be equal to minus lambda n plus n minus 1 minus m for positive lambda. So it means that in principle we can remove box which we do not have. We can have a negative row. Lambda n can last row can start to be negative. This happens only for last row. So this boundary term appears only for delta, only in case where n minus 1 minus m have the same residue as I think I minus 1. So only for one concrete E, we have the problem. We have the problem that in principle we can have the problem with battery. Okay. in principle, in terms of combinatorial diagrams, now not difficult to write down formulas for chi, for action of the key, to be q in some power on lambda. And I have not prepared the exact formula, so I will not write. Up to this small issue, the formulas look quite clear, quite nice in terms of the partitions. And actually, this is our preparation to the limit. Now let's talk about limit. Let us define for a map phi n plus delta n, which acts from the nth power to the maybe not delta, maybe some b, another capital n to the n plus n. And the map is defined as follows. So we take lambda and map it to the lambda wedge e minus n lambda nm. So this map actually depends on m. And map it to lambda n plus m. So this identity map on the partitions. Another way to state this map is the following. So some vector w goes to w wedge some tail. Tail should start from the point where this tail stopped. So first we have n minus m, then dot, then e n plus m minus 1 minus. And now we define the semi-infinite wedge space definition. Be a limit of how this is called direct limit. So we have maps lambda 1, maps to lambda 2, maps to lambda 3, maps to blah, blah, blah. And in the limit, this is a lambda infinity. So this is a set of sequences which stabilizes, this is a set of sequences, so element of the lambda semi-infinite wedge is a set of elements which belongs to all this, which belongs to all these spaces. I mean, not necessarily all, which belongs to the spaces such that they maps to each other using this phi. So this maps this is phi to 1, this is phi 3 2, and so on. Maybe I should say that there is a property even before this definition. Well, this obvious property that phi n plus m plus k n is the composition phi n plus m plus k n plus m phi n plus m. This property allows us to define this projective limit, yes, injective limit, directly. Maybe a bit informally, one can think that maybe formally. So basis in this space is formed by the elements lambda. Now we have only one index m, which is a product e minus lambda 1 plus minus m, which e minus lambda 2 plus 1 minus m, which, and the product becomes infinite. So we define these representations as the limit. Now we define the space, and now I'm going to claim that these are actual representations of affine quantum algebra. So this way to obtain, and this is no finite dimensional representations, and even no significant. I mean, before we have also not finite dimensional representation, but they are more close because we just take evaluation parameter to be formal parameter, not number. But now we obtain essentially finite dimensional representations. It will be integrable representations of level 1. So now we are going to define an action. And the action is given by the following. So, so this is, maybe should be stated in theorem. Formulas is like this, that Fi on lambda is equal to sum over boxes, over addable boxes of color I q in some power lambda plus s for E we have the same formula, but now summation goes over removable boxes, and I believe here color should be I minus 1. No, sorry, yes, color should be I. No, minuses, and for K, Ki acts by some diagonal formula. Defines action of the UQ SLN on this semi-infinite wedge space. Okay, I will discuss. So the proof is actually the following: that we know that everything is okay in finite case, and then we just take the limit. The Ross inverted maybe looks somehow good, but actually there is a problem with the story about limit, and I'm now trying to explain what is the main issue to overcome in this proof. I put it as a remark, and I will see maybe I wrote the sketch of the proof in notes. So first, let us look for formulas for Fi. Formula for Fi, I just copied the formula which we had in finite dimensional case. So from first class everything is okay, but recall that I completely ignored these powers of Q. In order to state that everything is okay, I have to note that these powers of Q do not depend on n capital, or at least they stabilize. So after if n capital is sufficiently large, they do not depend on n capital. Then this formula is okay. And this is actually true. So this powers I, maybe I put I. No, not I, let me put S. Okay, let me do not put anything here. So if box S, which we're trying to add, is some J lambda J plus 1. How do okay, I don't know. Maybe this is lambda J plus 1. This is a box which we are going to add. Then corresponding Q in this power depends on lambda i's for I less than equal than J. Indeed, look to the formula for F. We add J is number of places where we act. I have problem with indices. Let me write here J prime. So it depends on the previous part of the diagram. And this is because in the formula for the product of F, if we have F on say J's place, then we get K's only on previous places, which acts on the E's with previous numbers. So this property holds. Now B. Issue number B is the following. So this is not true for E, because for E we have coproduct is different. It has E times K times K. So okay, let's say the same for E. If this box which we are going to remove is this one, then this Q actually depends on lambda J prime with J prime greater than equals than J. And if we increase our n capital, then we add new lambdas, lambda J, which are equal to 0, but they are new. So in principle, we could have some problem. Let me show you an example. Let us take the following. Let us act by E1. If we act on E1 0, we get E1. If we act by delta of E1 of E0 which E1, we get the only term which will actually act will be E1 times K1 on E0 which E1. So, and K1, Okay, believe me or not, it will be k minus. Maybe I should add some diagram here. So let me put here n equals 3 for simplicity. Here minus 3, here will be minus 2, here will be minus 3, here we will be again minus 3, and will be q inverse e minus 2 wedge e1. Now if we get x by delta of e1, and then we get more. Then the only element which will act and it will equal to q inverse e minus 2 wedge e1 wedge e2. If we add one more term, so you see I'm discussing stabilization. I add such elements, then in this case we will have actually two terms. So we first we get the term. Okay, let me write it. We get the term like before, and plus we get actually this term. Because now E1 can act on this E3, whatever it means. And now we get E minus 2 times. Okay, maybe I will not do more calculations now. But what I want to say is that first of all, in principle, we can have some extra term which is related to boundary, as I actually said you something. Second of all, even for terms which we, in principle, of course, our ideas will be to ignore these extra terms, but if we live in the, but in finite case where relation holds, they appear. So it is not real why we ignore these terms, the relation will also hold. The second problem is that actually this the coefficient which in the simple term, which just decrease this index, just remove one box from our diagram, actually depend on n capital. Here it is 1, here it is q inverse, here it is again 1. And what is should be correct coefficient? And resolution is the following. So if we want to act on delta E1 in the limit, and limit is E3 times E1 times E2 times E3 times blah, blah, blah. Then we should look to this part to all these terms like E3 times E4 and then E6 times E7 and so on. They actually contribute 1. They should look to them somehow together. Or another way, I would say that we take the coefficient which appears mostly here. Almost always the coefficient is q inverse. So we take this coefficient in the limit. So this should be q inverse. So if we act by E1 on the diagram which corresponds to the triangle, we get q inverse. But this is not directly limit statement. This is a part of our definition. We should ignore the boundary term, and so we take take the coefficient which appears mostly in the form. This is our definition. Therefore, there is something to prove. Okay, this was about ease. And actually, if we have to somehow work to define ease, then it is natural that we have to work to define case also, because case are commutators of E and F. So if F is simple and E requires some redefinition in the limit, then case also should require some redefinition in the limit. And let me again explain this difficulty on the example. So if you want to act by K1 on this on the same element as we had here, E minus 3, which maybe here should be Q in positive power. Whatever it. Yes, I believe it should be Q in. Sorry, I'm thinking. Yes, I think, yes, no, I think it's correct. Should be Q, there should be Q in positive. On this E1 times E2 times blah, 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 this is our tail. Then it is clear how K1 acts on the initial part, but it's if n minus how to say its action is not in principle. This could differ from the action if we add also En. So K1 acts non-trivially on E's with the index which has residue 1 and residue 0. So in general, the eigenvalues here and here are the same. But if we somehow go through this residue equal to 0, then at some point this eigenvalue increases by 1 and then it drops by 1. And again, the definition is follows. We say that K1 acts as a DEX in general for generic. If n is not residue 0, residue 1, and so on. So if I take some infinite limit, then K1 acts on E minus 3 and acts by Q. It acts by Q inverse on E1 and acts by Q, then on E2 and acts by 1, and then we get pairs. Let me write it maybe explicitly and it will be clear, at least for me. So in E minus 3 it acts by Q inverse, in E4 acts by Q, then 1, then again Q inverse, Q1, and so on. So we take these pairs. We have, so if we want to act on K1 on this product, actually we should take the infinite product, all these terms which are not ones. But we somehow assume that this and this are just to cancel each other. So after the place where we actually have tail, then the contribution tail is equal to 1. This is the definition of the action of K, and actually it's the same definition we had. It agrees with the definition. Okay. Are there any questions? I didn't write explicit formulas here. I will write them in final notes. Now I spent one slide, even more, to explain from where this powers come from and what is the difficulty in the limit. Difficulty is, as usual, that we have to define the infinite sums sometimes, and we have this difficulty for E and for K. So what kind of representation we obtained in the limit? I am claiming that in the limit we obtained level 1 representation. What does it mean? So it means that if we take our vacuum, it can be any vacuum. So let's take, for example, a vacuum which corresponds to empty diagram and M. So it is E minus M, which E minus M plus 1, which then if we act by K1, K2, Kn on this vacuum, we get Q. So how to see this? Let me for simplicity take M equals 0. So we get E0, E1, E2, E3. Let me recall M and call this example. And then if we act by K1, what do we get? We get here we get Q inverse 1, Q inverse 1, and so on. If we act by K2, we get maybe Q inverse. I'm not sure. Maybe this should be Q inverse Q. Yes, should be like this. Yes, if we act by K1, if we act by K2, here should be Q inverse Q, 1, Q inverse Q, and so on. And if we act by K0, then have is Q, 1, Q inverse Q, 1, Q inverse, and so on. And we consider all this as a tail, but this Q remains. So this is why product of K's acts on the highest weight vector by K. And actually, we can compute any of K. So Ki acting on M is equal to Q in power A mod I on M. So it will be we get highest weight, which so highest weight will be fundamental. Only one of the K's acts by Q, other acts by 1. Get fundamental level 1 representation. Okay, I should stop more or less soon. So I have actually two more points in my plan, which I wanted to state, and so I just state them and finish. So first point is that we get a fundamental representation, but actually we obtain not irreducible representation of the affine quantum group. So the space which we defined, semi-infinite weight space, not irreducible for UQ of SLN hat. But it is reducible for algebra where we add additional Heisenberg algebra to UQ of SLN. So actually obtain not SLN representation, but GLN representation. And where this Heisenberg comes from, and this Heisenberg is limit of operators bk, which is sum of yi's in power k from y to z to n in affine Hecke algebra. So affine Hecke algebra, I almost kill affine Hecke algebra because I would take antisymmetrizer. But actually, some part of affine Hecke algebra commutes with antisymmetrizer. It's more or less its center. And such elements for k integer commutes with affine Hecke algebra. So they act on the antisymmetric space and they act in the limit. And in the limit, they actually become in the affine Hecke algebra they commute because they just, you see, the sum of the y's when y's commute. But in the limit, it appears that they become Heisenberg algebra. And one more point which I wanted to state, just not to have some words, that, and this is actually used in the proof that B's are Heisenberg algebra and find commutation relation, but I will not discuss the proof. Maybe I'll give it a problem, so just write something. But there is one more notion which I really want to mention. It is the notion of the vertex operators. We have operators which are denoted by k, which acts from the lambda n q to lambda n plus 1. Namely, k takes any w and maps it to ek which w. We have such naive operators. And first property which we need, that they're intertwiners for uq SLN. And it's usual to convenient to construct from them current. And, so the end is in usual story in the affine quantum group, matrix element of such current satisfies something like Nizhny-Zamolodchik QKZ equation. But anyway, I have no time to talk about it now, at least. In some other language, I hope we will see these vertex operators next time. Okay, I'm over time. I have to stop and I stop. Are there any questions?